ranking acids and bases. That'll be the topic in this lesson. Now, we just had an introduction to acids and bases in the last lesson, and now we're really going to learn all the different structural features that allow us to actually compare the relative acidities between two acids or the relative basicities between a couple of bases as well. Now, this is my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one of these, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new video. So ranking acids and bases, and I just want to start off with a little reminder from our introduction in the last lesson that the stronger an acid, the weaker its conjugate base, and vice versa. So if you have a stronger conjugate base, you're going to have a weaker acid associated with that. And so next part of that is going to be that a more stable base is a weaker base. So that's the next part. And then more stable base is usually going to mean lower energy electrons on the base. Now recall that Lewis's definition of base was an electron pair donor, and usually lower energy electrons mean more stable electrons, less reactive electrons. We'll see one major exception to that, but most of the time, that's kind of how we're going to rank bases. We're going to look at how low the energy of the electrons are and their relative stabilities associated with that. So lower energy electrons, more stable base. More stable base, weaker base. All right. So we're going to use a little mnemonic here, and in this case I'm going to use ARIO. But the truth is we only use ARIO if we're comparing bases. First off, these are a mnemonic for comparing bases, but we only use it if we're comparing a bunch of bases that all have the same charge. Now, and most of the time we'll be using bases that have a negative charge, but this could apply to comparing bases that are all neutral in charge and things of this sort as well. So I really want to put charge at the top of the list, although it's not a part of the proper mnemonic. Now, other textbooks and professors will often use a version of this mnemonic that includes charge, and they would call it cardio. And induction here, instead of calling it induction, they might call it dipole induction, so they can put the D and the I on that, because cardio is just a really cool one. So, and it starts with charge. So charge is really important. We'll get into that in a little bit. And then the atom actually acting as the base and where it's located on the periodic table, that'll be important in determining relative basicity. And then resonance, we've learned about resonance stabilization and how that could stabilize a base and make it a weaker base as well. And induction is one we haven't specifically talked about yet. Maybe you saw it in Gen Chem, maybe you didn't. Depends on your class. But induction means, do you have any electronegative atoms nearby? So that might help stabilize a base. It turns out having electronegative atoms are going to pull electrons towards them and lower the electron density on that base, making it a more stable base, less negative sort of thing. We'll get more into that in a little bit. And then finally, orbitals. And this last one really should be called hybridization, because it's really a difference in hybridization of the orbitals of where you find a lone pair of electrons. But that wouldn't make a good mnemonic, or something like that. So ARIO, they go with orbitals, but it's really a matter of hybridization. But this little mnemonic is the one we're going to use, and you typically follow it in order. And most of the time, again, 99% of the time, you're just going to be comparing a bunch of bases that all have the same charge. And so this little charge rule becomes irrelevant. And that's why it really just reduces down to ARIO. But for that one time out of 100, I put the charge at the top of the list here. So let's take a look. We're going to take an in-depth look at every single one of these rules so that you can rank acids and bases and their relative acidity or relative basicity just based on looking at their structures with no pKa's provided. All right, so charge here. So it turns out when you get a negative charge, that raises the energy of the electrons. When you have more electrons around that oxygen nucleus, they can't get as close to the nucleus because they're repelling each other, and so they spread out. And the further they get out from that nucleus, the higher their energy and the greater the reactivity as a base. And so having a negative charge causes your electron cloud to be bigger, the electrons are on average further from the nucleus, and it leads to a stronger base. Now, a positive charge is going to do the exact opposite. If I was actually talking about this guy as acting like a base here, that lone pair, because now we have a positive formal charge in the oxygen with fewer electrons around the nucleus, which means the remaining electrons can actually get even closer to the nucleus, which lowers their energy and makes them less reactive. And so in this case, if we were going to look at a trend in basicity, so it would be going to the left. And if we want to talk about the stability of the electrons would actually be getting more stable as they went to the right. So and that would relate to basicity here. So it turns out for charge, though, you could also look at this in terms of acidity in this one case. And notice we've got hydronium over here, hydroxide over here. We know hydronium's a strong acid. We know hydroxide's a strong base. And we got water right in the middle, which is neutral. And so you could look at this like so. Cool. So charge in this one example here, this set of examples, is you got to be careful on when it's relevant, because it's not going to always be relevant. Now, as long as you're comparing a conjugate base to a conjugate acid to conjugate base, that's when charge will work every time. As long as you're just comparing a conjugate acid to a conjugate base, yes, whichever one of these is more negative is the better base. Whichever one of these is more positive or less negative is the better acid. That's when it works. Now, if you're trying to compare just two totally different molecules that have a different charge, maybe it'll work and maybe it won't. And it's not a comparison that comes up a lot as a result, because it's hard to ask you about it. Now, if it involves one of the acids that you're supposed to memorize the pKa's for, one of those typical functional groups that we went through in the last lesson, well, then by all means, that's fair game, and you wouldn't even need to use rules, and you shouldn't use rules in that case. And I'll show you a couple examples where that happens. But I just want to point out that charge is important, and it's probably the most important thing. However, most of the time, you're not going to be comparing acids or bases that have any difference in charge. And so most of the time, this will just be a moot point. But I did want to cover my bases, and I definitely wanted to relate it to the energies of electrons as well. And again, negative charge, higher energy electrons, positive charge, lower energy electrons. Okay, so now let's get into that mnemonic proper. So once you verify that what you're comparing has the same charge, you next kind of follow this mnemonic in order. So the first rule you'll consider is atom. And if you don't find a difference there, then you'd move on to resonance. And if you still don't find the distinguishing difference there, you'd move on to induction. And if you still don't find the distinguishing difference there, you'd move on to orbitals. So these are ranked kind of in like order of priority. So the atom rule is the most important, again, after charge. But then resonance, then induction, then orbitals. And again, this is not a perfect set of rules, and there is no perfect set of rules. But this will work usually, at least 90% of the time. This will lead you to the right conclusions as far as relative acidity and basicity. And when these won't lead you to the right path, that's why we memorized some pKa's earlier, because that would kind of take care of those exceptions. So before I ever use these rules, if I'm ranking acids, I look at pKa's first, the ones I've memorized. But if I don't know the appropriate pKa's, then I go to my rules and rank my relative acidity and basicity. So this atom rule, the way this works, if we look at relative basicity on the periodic table, and I know you can't see the whole periodic table, but I just needed you to be able to see the non-metals that'll show up in our organic compounds. And it turns out basicity increases as you get smaller and as you get less electronegative. And there's two parts to this. So the vertical part of that trend is all about size. And it turns out a smaller base makes a shorter bond to an H plus ion, and a shorter bond is a stronger bond. And so as a result, the smaller base is the stronger base. And then finally, as you go from right to left within a period now, if you're comparing elements within a period, it's not about size anymore, because they're all really close in size, and it turns out to be more about electronegativity instead. And it turns out the less electronegative base is the less stable base and the stronger base. So as long as you're comparing in the same group, your comparison is about electronegativity. As long as you're comparing in, and I said that backwards, as long as you're comparing in the same period, it's about electronegativity. But if you're comparing within the same group, it's about size. So that's kind of the deal here. So you got to remember which is which, but they're both important. But notice size must be more important, because again, if you're comparing them in the same period, the more electronegative it is, it's a weaker base, the less electronegative, the stronger base. But in the same group, the more electronegative is actually the stronger base. That's how we know that size must be more important consideration. But again, if you're comparing them in the same group, it's about size. If it's in the same period, it's about electronegativity. All right. Incidentally, with electronegativity, you can totally correlate the energy of the electrons. When you have like a negative charge, let's say, or just lone pairs on a more electronegative atom, it pulls them closer to the nucleus, which lowers their energy and makes them more stable in a weaker base. Now, in size, this is the one place where the energy of the electrons does not correlate with basicity. So it turns out the larger atom has higher energy electrons, but it's still the weaker base. Because it turns out the energy of the electrons is not the whole story, but most of the time it's an adequate story. But this is the one example where it's not. When you're comparing atoms here in the same group, size is more important. And instead of just worrying about the energy of the electrons, it's also about the process of acting as a base, of making a new bond to H+. And again, those big atoms, they just make really weak bonds to H+, and so they're not good bases, it turns out. And so as a result, the energy of the electrons, not a good reflection in that one comparison. Again, comparing different atoms in the same group. But outside of that, the energy of the electrons and will correspond greatly with basicity. Lower energy electrons, weaker base. One exception there. All right, so again, bases get stronger as we go up the periodic table and as we move to the left. So if we make some comparisons here. So in this case, we're going to first compare these two, and I just want you to circle on your study guide there which one is the stronger base. And in this case, I can see oxygen is smaller than sulfur. They're in the same group, so it's all about size. And the smaller base is the stronger base. So we're good to go there. And in the next pair, again, circle in the stronger base. Now it's between oxygen and nitrogen. And now these are in the same period. So now it's about electronegativity. Oxygen's more electronegative. That makes him the weaker base. Nitrogen's less electronegative. That makes him the stronger base in this pair. Cool. Now at the same breath, I also want to compare and rank some acids here. And the problem is from ARIO here doesn't help you rank acids directly. The rules ARIO here are going to be for ranking bases. But this is where the idea that the stronger acid has the weaker conjugate base and vice versa comes in handy. Because if you're asked to compare acids, and that's what I'm asking you over here now in these pairs, what you're actually going to do is look back and draw out their conjugate bases if you haven't already. Notice this is the conjugate base of this one, and this is the conjugate base of this one. And so if you're comparing bases, that's what the rule's for. You don't have to draw any conjugates out or anything like that. But if you're comparing acids, first thing you'd ever do is draw out the conjugate bases. And you look at them and be like, okay, who's stronger over here? Well, he's stronger. So if this one is the stronger base, well, then he comes from the weaker conjugate acid. And if this is the weaker base, the weaker, more stable base, then he comes from the stronger conjugate acid. And so we're not actually ranking the acids directly. We're only ranking them in the context of having already ranked their conjugate bases. So when you're asked to rank bases, good to go. That's what the rules are for. But when you're asked to rank acids, you're going to do it indirectly every time. So, well, almost every time. But you're going to do it indirectly most of the time by looking at the conjugate bases instead. Same thing here. So here we circled the stronger base. And if this is the stronger base, it has the weaker conjugate acid. So if this was the weaker base, he has the stronger conjugate acid. And so a lot of times when we're ranking acids, we just say, okay, which one of these has the weaker, more stable conjugate base? In this case, it was sulfur. And in these two, if I said which one again has the weaker, more stable conjugate base, in this case, it was oxygen. Now up here, it was the weaker conjugate base because sulfur is bigger than oxygen. And down here, so the weaker, more stable conjugate base was oxygen because oxygen's more electronegative than nitrogen. Cool. That is your atom rule. All right, so after atom is the resonance rule. And again, these rules for ranking bases, and resonance simply stabilizes bases. That's the way it works. So if you have something with resonance and something without, well, the thing with resonance is generally going to be more stable, assuming you've already done your atom rule. So again, we would never start out with the resonance rule. We'd first verify that the bases we're comparing all have the same charge. Then we verify that they're all the same atom acting as the base. And then we'd move on to resonance. So if we look at the example here, we're going to compare these three bases. And I've drawn out all the resonance structures here. And so in this case, the first question would be, do they have the same charge? Well, negative charge, negative charge, negative charge. Done. Cool. Then we move on to the atom rule and say, which atom actually acts as the base? Well, it's oxygen here, it's oxygen here, and it's oxygen here. And so we have a tie. And so then we'd have to move on and go to the resonance rule. So that's kind of how this works. So you wouldn't start with the resonance rule unless you've already done the charge in the atom rule first. All right, so doing the resonance rule now, we see that here the negative charge is no resonance. It's on a single oxygen completely. Here, the negative charge due to resonance is shared between two oxygen atoms. That makes it more stable, and a more stable base is a weaker base. This is a weaker base than the first one that has no resonance. And then finally, this last one, the negative charge is actually shared on three oxygen atoms and is even more stable. And even more stable means even weaker base. And so if we were to rank these as bases, with one being the strongest and three being the weakest, well, our most stable base is our weakest base. And let's do this in blue. So, and then our strongest base that had no resonance, number one, and then obviously this one that had two resonance structures sharing on two oxygens was number two. Now, something you should know about comparing resonance, it's not just about the total number of resonance structures, it's also about the quality of resonance structures. Because if you notice, like here, I'm sharing the negative charge on two oxygens, and here it's on three oxygens. Well, that's an easy comparison. But what if the negative charge was shared, like, instead of on two oxygens, what if it was shared on one oxygen and three carbons? Well, carbon's not as electronegative as oxygen. It's not as good of a place to put a negative charge. So you got to ask yourself, is it two resonance structures sharing it on two oxygens better, or is four resonance structures, but it's only one oxygen and three carbons better? Well, I don't expect you to know that. Well, it turns out sharing it on two oxygens is better. So But again, that's one of those examples where you're just kind of, until you've seen it worked out for you, you just don't know. However, that's exactly the situation we have when we compare a carboxylic acid to a phenol. But if you've memorized your pKa's, you'd know that a carboxylic acid has a pKa of 4 to 5, a phenol has a pKa of 10, so the carboxylic acid is stronger, and you wouldn't have to rely on the rules for an example that's a little bit challenging because you've memorized some pKa's. So just wanted to point out where that might come in handy. Okay, so we've ranked some bases. Now, what if I asked you to rank these acids? And so for these acids, notice these are just the conjugate acids here. And if you were asked to rank these acids, first thing you'd want to do is draw the conjugate bases if you didn't have them already on the board like I do. So we've got them on the board now. And in this case, you just know that the acids have the exact opposite ranking. So the strongest acid has the weakest conjugate base. Well, the weakest conjugate base was this one. It was the one that was most stable due to resonance, the weakest base. So then this must be the strongest acid. We'll make him number 1. And it's just the exact opposite ranking. Our strongest and least stable base comes from the weakest conjugate acid. Cool. So, once again, you can rank bases directly. That's what the ARIO mnemonic and the rules are for. But acids we rank indirectly by looking at the conjugate bases and just knowing, again, the stronger the acid, the weaker the conjugate base, and vice versa. All right, the next rule in our ARIO mnemonic is induction. So an induction deals with polarity. Now, for now, I'm going to look at things that are simply electronegative, and we like to call them electron-withdrawing when they're electronegative because they're pulling electrons away. And if you recall, we talked about charge at the very beginning. We said that something with a more negative charge is a stronger base, whereas with a less negative charge, i.e. more positive charge, would be a weaker base. And so what an electronegative atom does is it pulls electron density away from a base, making the base less negative and therefore more stable, lower energy electrons, and a weaker base. Cool, we'll find out later on in the course, not in this chapter, that in addition to electron withdrawing groups, there are also things called electron donating groups, and they're not going to really have much relevance here, but they will have some relevance down usually in the beginning of second semester when you study alcohols and phenols. All right. So let's go through our list. And again, we wouldn't ever start with induction as a rule. We just work our way down. So first thing I want to look at in comparing the first pair here, I want you to circle the stronger pair, or the stronger base in the pair, is charge. Well, they're both -1. Then go to atom. Well, oxygen is the base in either case, the atom with the negative charge, so no difference there. So then we move on to resonance. Well, these are both the conjugate bases of carboxylic acids. They're both going to have two resonance structures and share the negative charge between two oxygens. We still have no distinguishing difference. And so now we move on to induction. And so we've already identified that oxygen is the base. That's the atom rule. Don't get that confused. A lot of students confuse the atom rule and the induction rule. My question now is, now that we know oxygen is the base in both cases, are there any electronegative atoms nearby that can act as a helpful neighbor to help stabilize the base? And over here we've got chlorine, and over here there's nobody electronegative around those oxygens at all. So again, those oxygens are sharing the negative charge by resonance. They are the base. And if you are the base, that's what the atom rule is about. And the atom rule is about size and then electronegativity. But induction here means you're not the base, you're just a helpful neighbor, and you're in the area to help that base out. And it has nothing to do with size, it has everything to do with just pure electronegativity, pure polarity, if you will. And so in this case, the chlorine here is going to pull electron density, so away from this carbon technically, which is then going to pull it away from this carbon, which then pulls it away from this carbon, which is then going to pull some away from those oxygens, eventually making those oxygens less negatively charged, which makes them more stable, lower energy, and a weaker base. So the one stabilized by induction is the weaker base. Okay, so that's the first part. So, and again, induction's all about electronegativity, so far as we're concerned with in this lesson. All right, in the next example here, so we're going to go through the rules again. Charge, no difference. Atom, oxygen in both cases, no difference. Resonance, stabilized by resonance between two oxygens in both cases, no difference. So we make it to induction. And we ask, do either of these have a helpful neighbor nearby? Well, yeah, they both do. And they have the same neighbor, chlorine, which is equal in electronegativity. So, however, if you notice, by the way, we pull electrons from the adjacent atom through the bonds based on electronegativity. So if we were like 100 carbons long, and then there was just a chlorine way over here, do you think the other side of the molecule would even know there's a chlorine down there? No. And so proximity is really important as well. Typically, the closer it is, the bigger the impact it's going to have in terms of stabilization. So in this case, the chlorine is closer to these oxygens. It's only 1, 2, and then 3 bonds away, whereas this one is 1, 2, 3, 4 bonds away from the oxygens. And so the closer it is, the more stabilizing of an impact, the greater its stabilization due to induction. And so that makes this the more stable base, and the more stable base is the weaker base. So the one that's less stabilized is the stronger base. All right. So now we've learned having an electronegative atom in the area is helpful, and the closer it is, the more helpful it is. And so now, what if we have 2 different helpful neighbors carrying out inductive stabilization here? So once again, charge, no difference. Atom, oxygen, oxygen, no difference. Resonance, shared between 2 oxygen, 2 resonance structures on both, no difference. So then we make it to induction. And now there is a difference. Now they're in the same location, they're the same distance away from the oxygens, from the bases, but one's chlorine and one's fluorine. And this is one of the most common mistakes students make, is they say, okay, but Chad, you just told me that fluorine was a better base than chlorine. No, 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 no. I told you when fluorine is the base, is the atom acting as the base, that it's a better base. But again, here, fluorine and chlorine, they're not the base in either one of these. The oxygens have the negative charge. They're the base. Fluorine and chlorine are not acting as the base at all, but they can help stabilize the oxygens who are acting as the base. And again, your ability to help stabilize those oxygens has nothing to do with how big you are, only with how electronegative you are. And fluorine is more electronegative than chlorine. And as fluorine is more electronegative than chlorine, this will be a more stabilized base. That negative charge will be diminished more on these oxygens than on the oxygens on the molecule next door. And so as a result, the more stable base on the right here is the weaker base, more stabilized by induction. So the one on the left is the stronger base. Cool. Can't emphasize this enough, though. So the difference between the atom rule and induction. The atom rule is you're examining the atom that's acting as the base, which in our case was oxygens in both cases. No difference. Induction, though, is you're looking for a helpful neighbor who's near to the base, and it's all about electronegativity. So the atom rule is about size first and then electronegativity. Are you the base? Then we're going to talk about your size and then your electronegativity. But if we're talking about induction and you're not the base, you're just nearby, you're in the neighborhood, it's purely about your electronegativity. Your size is irrelevant. All right, finally, last example here. And in this case, same comparisons, same charge, same atom, same resonance, comes down to induction again. And 2 fluorines is better than 1, so to speak. So 2 fluorines, 2 electronegative atoms, will have even more of a stabilizing impact than 1 fluorine. And so this will be the even more stable base, and therefore the weaker base. Therefore, this one is the stronger base. Cool, so now I've given you an example of every kind of comparison you might see. And again, we only compared 2 at a time. You might get 3 or 4 of these and be asked to rank them in order. Well, everything that's important just came up. Do you have an electron, withdrawing group and one doesn't? Do you have both the same electron withdrawing group, but one's closer, one's further? Or do you have 2 different ones and one's more electronegative, one's less electronegative? Or do you have more electron withdrawing groups versus another? Those are the typical comparisons you're likely to see. Okay, so I didn't want to clutter up the board initially, but in addition to comparing these lovely bases, now we're going to go compare their conjugate acids. And again, the key is, the rules are for bases, and we just jumped right into comparing the bases. But if you had been asked to compare any of these pairs of conjugate acids first instead, well, the first thing you would realize is oh, they're asking me to compare acids. I don't compare acids. I would draw out their conjugate bases and then compare those. And fortunately, we can already take advantage of the fact that we've done that. And so we're already ready to compare these because we've already compared the conjugate bases. And so in this case, in the first example, in these 2 conjugate acids, I would again draw out their conjugate bases. I'd realize that this one is the more stable conjugate base. The more stable conjugate base is the weaker conjugate base, and the more stable, weaker conjugate base comes from the stronger conjugate acid. So now we're circling the stronger conjugate acid. Same thing in the next example. We already figured out, again, in comparing these 2 acids, we already figured out the relative basicities of the conjugate bases. So this had the chlorine closer, which had a more stabilizing influence by induction, and the more stable base is the weaker base, and the weaker base comes from the stronger conjugate acid. Cool, next comparison, again, we're comparing these 2 acids. First thing you'd do is draw out these 2 conjugate bases. And here, fluorine was more electronegative than chlorine. And so fluorine is going to pull more electrons away from the oxygens, making them less negative and more stable. And more stable means weaker base. And the weaker base, again, comes from the stronger conjugate acid. And finally, in the last example, we found out that 2 fluorines was more stabilizing than 1 fluorine. So this was the more stable base. The more stable base comes, once again, from the stronger conjugate acid. Cool. So obviously very fortunate that we already had the conjugate bases on the board and we already had them ranked. But if we hadn't, that would have been the first thing we'd have to do. So the last rule in our mnemonic is orbitals, so the O here. And once again, you wouldn't just jump into using this rule. You'd first have to verify that there's no distinction made between the rest of the rules in the comparison that you're making. So, and again, it's orbitals here, the O for orbitals, but again, it really refers to a difference in the hybridization of your basic atom. So if we take a look here at comparing these 3 lovely bases here, first thing we do is say, do they all have the same charge? Yep, -1, -1, -1. Okay, no difference there. Then we move on and talk about the basic atom, and it's carbon compared to carbon compared to carbon. Okay, atom rule doesn't help us either, so we'd move on to resonance, and it turns out none of these are stabilized by resonance. So if you look, you might go like, Chad, wait a minute, what about like this guy? Well, again, when your lone pair of electrons is exactly 1 bond away from the pi electrons, i.e. like allylic or benzylic, that's when you can expect resonance. But here it's not 1 bond away, it's right where the pi electrons are. So no resonance in any of these. So move on to induction. Are there any electronegative atoms in the area to help stabilize this? Nope, not in any of the cases. So finally, we move on to orbitals. And we say, is there a difference in the hybridization of the basic atom in all these cases? And there is indeed a difference. So this carbon right here has only 2 electron domains. It's bonded to 1 atom and has 1 lone pair. So it's going to be sp hybridized. So this carbon right here is bonded to 2 atoms, a carbon and a hydrogen. Maybe I'll draw that hydrogen in to make this a little more obvious. So it bonded to 2 atoms and 1 lone pair, 3 electron domains, sp2 hybridized. And then finally, this one right here is bonded to 3 atoms, a carbon, 2 hydrogens, and then it has a lone pair, 4 domains, is going to be sp3 hybridized. So there is a difference in hybridization, and it turns out that's a significant thing. Now, if you kind of look at the difference between an sp, an sp2, and an sp3, so your sp is 50% s, 50% p. We'd say 50% s character, and probably looks like something like this. Your sp2 is now only 33% s, 1/3 s, 2/3 p, and resembling more like a p orbital now, only 33% s character. It's a little longer, and the electrons are going to be a little further from the nucleus at the node there than they would be if they were in an sp hybrid orbital. So having a lone pair in an sp, as compared to having a lone pair in an sp2, they're going to be on average closer to the nucleus in an sp hybrid than in an sp2. And then finally in an sp3 hybrid orbital, it's even elongated even further, and so the electrons on average are going to be even further from the nucleus and be even higher energy and less stable in an sp3. And so the idea then is that your lone pair is going to be most stable on an sp hybridized carbon as compared to an sp2 or an sp3. And if here it's most stable, that makes him the weakest base, which we'll put number 3 in this case. And then here on the sp3 hybridized atom, that lone pair is going to be the least stable, which in our case is going to mean the strongest base. And then this guy's in the middle. And so that's our trend for basicity. That's the orbital rule, really a difference in hybridization. And so if you were asked to compare the conjugate acids instead, well, again, you'd realize that I'm not comparing acids. And first thing you do is draw out all the conjugate bases, go through the rules, and come up with this relative basicity, which would then allow you to come up with exactly the opposite trend in acidity for the conjugate acids. So the most stable and weakest conjugate base has the strongest conjugate acid, so on and so forth. This rule doesn't come up very often, but it is something you're probably going to see at least once or twice between your homeworks and your tests. So now we've made it completely through the mnemonic, and we've kind of gone step by step, and we kind of knew what comparisons were coming because we were going in order. So now I want to work 3 examples, and with these 3 examples, we're going to do specifically comparing acidity. And we're going to keep in mind the pKa's we're supposed to know, as well as all these lovely rules. All right, so we've got 3 different comparisons here, and the first one's going to be this lovely species versus this one. And first thing you should do is keep in mind, what pKa's do you know? Well, this is a carboxylic acid, and his pKa is in the 4 to 5 range. usually. It's pretty typical. Whereas this is an alcohol, and its pKa is usually in the range of like 16. Now, the truth is, this one's got a chlorine that's going to inductively stabilize the conjugate base, which is going to ultimately make the conjugate base weaker and this acid a stronger acid. But 16 versus 4 to 5, it's not going to make it down that low. Not a chance. And so in this case, technically, you could just be like, yeah, there's my stronger acid. I circled it. Life is good. So, but if you didn't recall your pKa's or didn't categorize these correctly, again, you could always just draw their conjugate bases and be like, and use your ARIO mnemonic here. So in this case, you go through and say, do they have the same charge? Yep, -1 for comparing your bases. Then you'd say, okay, atom rule. Oxygen's the base and oxygen's the base. It's a tie. Atom rule didn't help me. So move on to the resonance rule. And we'd see that the one on the left has resonance and the one on the right does not have resonance. And so the one with resonance is more stable, and a more stable base is a weaker base, and a weaker base comes from the stronger conjugate acid. The rules would have led us to the same place. Cool, moving on to the next one here, and this is one I brought up earlier. So we've got a carboxylic acid here, and again, pKa of a typical carboxylic acid is in the 4 to 5 range, and this is a phenol, and pKa of a typical phenol is in the 10 range. And so we can say, yeah, we've got our stronger acid right here because we memorized some pKa's. Now this is the tricky one. Had you not memorized those pKa's, you'd have had a tough time with this one until you came across it somewhere along the way. And we've seen a carboxylic acid. It's got 2 resonance structures, shares the negative charge on 2 oxygen atoms here. But the phenol we haven't actually drawn out specifically, but the conjugate base actually shares the negative charge between the oxygen, and then it turns out 3 of the carbon atoms in the ring. I'm going to draw these out, but I'm not going to actually show you how to get there. I'll leave that on you for now. And finally, one more. You know what? I'm going to be a little nicer than I said I was going to be. So, and here, lone pair comes down, lone pair comes out onto that atom. Here, lone pair goes in to form a pi bond becomes a lone pair, getting you here. Here, lone pair becomes a pi bond becomes a lone pair, getting you here. All right, so the question we got to ask yourself, a lot of students get this one wrong because here they're, oh, more resonant structures, more resonance, more stable base, weaker base comes from the stronger acid, but we saw that wasn't the case at all. But we're not comparing apples to apples here, so you can't just compare the absolute number of resonance structures unless the negative charge is just being shared on the same atom every time. Well, that would work. So, but here, sharing the negative charge on 2 oxygens as compared to sharing the negative charge on 1 oxygen and 3 carbons. And there's no intuitive way to just be like, well, I have a hunch. So it really does come down to either having seen this example before or just knowing those pKa's. Super helpful in this case. It turns out sharing it on 2 oxygens was more stable. That was the weaker base, which came from our stronger acid. All right, finally, this last one. This last one is a super tricky example, but you might remember pKa's here, and pKa of a terminal alkyne here was right around 26. So, and we didn't cover this guy's pKa explicitly, but we did cover a very similar molecule, and that similar molecule was ammonia, and we said ammonia's pKa was right around 38. And so whether you deprotonate neutral nitrogen on ammonia or a neutral nitrogen on an amine, it's going to be around a pKa of 38. And I can see that my lower pKa is definitely this guy, and he's going to be our stronger acid. Cool, and I brought this one up on purpose because this is a tricky example. If you try to follow the mnemonic here, you're going to get hosed. Now let's see why. So if we draw those conjugate bases, so said at the beginning of this lesson that there's no perfect set of rules because there are always exceptions like this one. So if we look here and we start with charge like -1, life is good. So we move on to atom, we're like carbon versus nitrogen. Well, carbon and nitrogen are in the same period, which means it's going to be about electronegativity. And as nitrogen is more electronegative, we'd think, oh, more electronegative, more stable. More stable base, weaker base. Weaker base comes from the stronger acid, and we totally got the opposite determination from our pKa values that we knew. So what's going on here? So, well, it turns out this is usually the order of priority as far as what distinguishes two bases and comparing them in order of importance. So, however, there's two differences here. It is a difference in atom, but it's also a difference in hybridization of the orbitals. So it's not just comparing carbon to nitrogen, and that's the only difference. It's an sp hybridized carbon versus an sp3 hybridized nitrogen. And it just so turns out that the sp is more stable, the sp carbon is more stable than the sp3 nitrogen. Now, there's no intuitive way to have known that, but because we knew the pKa's, we didn't get hosed by this exception from our rules. So like I said, there's usually 2 or 3 comparisons you can make where the rules are going to lead you astray, but if you know all your pKa's, those can't get you. Cool. This is acids and bases and ranking them. And again, understanding relative acidity and basicity is really going to be key to understanding relative reactivity for when we start talking about chemical reactions later. I can't stress how important this is for getting a good working understanding of how the world works from an organic chemistry perspective, but how chemical reactions work. If you have found this lesson helpful, consider giving me a like and a share. That's, again, the best thing you can do to support the channel. And if you're looking for practice problems on acids and bases or the study guides that go with this, check out my premium course on chadsprep.com.